problem in nickel-based alloys is melting along the grain boundaries in the heat-affected zone, which then, because of the restraint that's inherent in welding, the residual stresses, those sometimes pull apart along those melted grain boundaries. There's two ways that the grain boundaries can get liquated or melted. One is a segregation mechanism, and the way that happens is there's solute or impurity elements that segregate to the grain boundaries because of the heat of welding. The diffusion is higher, and some of these elements can diffuse to the grain boundaries, and what happens is they suppress the local melting temperature along the grain boundaries. Another mechanism for the grain boundaries in the heat-affected zone to liquate is there might be a particle, or there might be just a region of the microstructure that has a lower liquidus temperature or a lower melting point, and that might get melted from the heat of welding. And then, like I said before, you've got grain boundaries that are moving around, and so sometimes you've got a particle or something that melts, and then you've got a grain boundary that sweeps along. And what happens is, as that grain boundary sweeps along into that particle that's melted, then the liquid can run along the boundary, and that's actually called constitutional liquation. The alloys, the gamma double prime alloys that are strengthened by niobium carbides can have that form of heat-affected zone liquation. So what I just tried to explain in words, I'll show you a picture of, and maybe it can be a little more clear. So this first diagram up here has to do with temperature versus time. So as you're making a weld, as you're on heating, you're allowing some of those alloying elements to segregate to the grain boundaries, and then also as you continue to heat, you start to melt some of those particles in other low melting regions. And then as you begin cooling, you're also still hot enough that you're allowing some of that liquation to occur along the grain boundaries. And so this one down here, this is the segregation mechanism. So this over here is the solidifying weld. You've got the solidification structure going on there. This over here is the heat-affected zone. This material was not melted completely, but right along the grain boundary, because you've got alloying elements segregating to that grain boundary, you can end up with a liquid film along that grain boundary, which can then pull apart. This is the penetration, or the constitutional liquation mechanism, where you had particles or low melting regions, and then as that grain boundary migrates and comes in contact with these, you also end up with the liquid film along the grain boundary. Well, it's pretty quick. I mean, when you think about making a weld, and you think about how fast that material melts and re-solidifies, I mean, it's happening in those types of time frames. So, microseconds, I suppose. So here are a few things that we can think about to try and prevent this liquation in the heat-affected zone. One is to minimize the grain size. What that does is it increases the grain boundary area and spreads the liquid around. So instead of having a few grain boundaries that are really wet by the low melting constituents, you've got a bunch of grain boundaries that might just have a little bit on there. The problem with that is sometimes in these alloys, like I mentioned earlier, you want large grain size to control creep, and so you've got to balance that. You can also make sure you've got low impurities, which will lead to those like-weighted films. And another thing that you have to balance with your creep properties is a lot of times they use boron additions to improve creep properties. Well, those very boron additions might increase your grain boundary liquation and increase your susceptibility to this type of heat-affected zone cracking. As with all of these, we want to minimize restraint as much as possible. We can do that with joint design. We can do that by welding in the solution annealed condition, as I mentioned before. Another thing that would be quite expensive but could be done is to butter the substrates. And what that is basically, if you're welding on an alloy that's highly susceptible to heat-affected zone liquation cracking, you might butter or weld over the surface or almost clad the surface with an alloy that is less susceptible, and do that under controlled circumstances. And that would be one method for preventing these cracks as well. So the last weldability issue with nickel-based alloys that I wanted to talk about is strain age cracking. This is a phenomena that only happens in the super alloys, or the precipitation strengthened alloys. And it happens because of that rapid precipitation of the strengthening precipitates, the gamma prime precipitate especially. It's similar to reheat cracking in steels, and the mechanism that has been put forth for this is that these precipitates of nickel, aluminum, and titanium, as you're welding, they dissolve because of the heat. And what that does is it leads to a softening of the weld metal and the heat-affected zone. And then after you've made your weld and you've created that softened region around the weld, you want to post-weld heat treat to restore the properties, and you get intragranular, which means within the grains, precipitation of that gamma prime strengthening precipitate. And so when that happens, you end up with strain at the grain boundaries because of that strengthening within the grains. And because you're strengthening the inside of the grains due to the precipitation, your grain boundaries are often then weakened, and you end up with cracking along the grains of the heat-affected zone. And that's called strain age cracking. That's a different phenomenon. It's actually, well, it's not exactly the same. I mean, it's intergranular. Well, they're both, the cracks are both intergranular. With sensitization, that's a stainless steel phenomenon, where you're actually forming carbides along the grain boundaries, and you're reducing the corrosion resistance of the boundary because you're pulling in the chromium into those carbides. Here you're actually strengthening the inside of the grain, which allows cracking along the grain boundaries. So a few ways to prevent strain age cracking. You can select a resistant material. Alloy 718 was developed much for this reason. It's strengthened by the gamma double prime strengthening precipitate rather than the gamma prime. So it's got lower titanium and aluminum. There's been research that has shown that by lowering titanium and aluminum in these alloys, you can form alloys that are resistant to strain age cracking. And so alloy 718 falls down here. This is kind of the boundary between resistant and susceptible. But by keeping your aluminum and your titanium low, thereby not forming the gamma prime, but forming the gamma double prime or some other strengthening precipitate, you can reduce the susceptibility to strain age cracking.
Mike, in that previous chart, you had wrought versus cast. I know there's a difference in the definition for wrought versus cast, like iron. This is really just forged versus cast.
Well, wrought is worked in some way versus cast. Yeah. Yeah. Let's see, back to preventing strain age cracking. You can also heat rapidly during post-weld heat treating to avoid the nose of the precipitation curve. Have you showed them curves with noses and things like that? So I'll put this back up here. But this one here, as you're heating during your post-weld heat treatment, the mechanism of formation of the precipitate takes some time, and so you've got these noses of precipitation curves. And so with a high titanium and aluminum alloy, that curve is actually over here, whereas with a low titanium and aluminum alloy, it's over here. And so it's much easier with something like alloy 718 to heat it and miss that curve rather than something that has high aluminum and titanium. You've got to heat it much quicker to miss the nose of that precipitation curve. And I don't really have a diagram to demonstrate the next one, but I'll put this back up and just talk about it. Another thing that sometimes is done, and it relieves some of the residual stresses, is to heat it up and hold it below the nose of the curve, and then just bring it through the nose of the curve quickly. That's another method that's used for relieving some residual stress and preventing strain age cracking. So one last slide. Much the same as with the other things that we've talked about. You can always reduce susceptibility to these various weldability issues with your design and your welding procedures. You can design to reduce residual stresses. You can use that stringer bead technique that I talked about, making a series of smaller welds rather than a large weld. You can use processes that put a low heat input into the material, and you can also try to minimize the PMZ, which is the partially melted zone, which is that region in the heat affected zone that's melted along the grain boundaries. You can also, as you're designing your structure that's welded, is you can just try to put your welds in locations that will not create as much stress or be in as stressed of a state. And as you do those things, you can reduce the cracking phenomena. The main thing to remember in all of those different cracking problems is if much I'm sure you could draw a Venn diagram for that too, but whenever you're pulling, whenever you've got restraint that's pulling on these, because of the nature of the way these solidify and the way that they melt, you're going to have regions of lower melting or even liquid. And so if you can minimize the pulling apart on that, then you'll be able to minimize the cracking that takes place. That's basically what I've got for that today. Are there any questions or comments? Okay. Like I told you before, I'd be happy to answer any further questions or provide you some additional material to look at if you're interested in these things. So just get in touch with me that way.